Hey everyone, welcome back to week 5, Graduate Statistics, University of Cincinnati. We're continuing with the guided activity, and we left off on the past video with the following question. Why should we even contemplate the null hypothesis that gender bias is not there, right, in promotion decisions, if a difference of 30% in promotion decisions is demonstrated in the data? So in order to answer this question, I asked you to consider the following scenario. Let's entertain the possibility that the truth is that supervisors in the real world are not influenced by a worker's gender, or I should say assigned sex, when making promotion decisions. What should be the difference in promotion decisions made by supervisors that receive male and female marked file, if that is true? Okay, what do you think? You probably had a little bit time to think before coming into this video, so I'll just tell you the answer. The difference, if there's no gender bias, there should have been a 0% difference, right? That's what's expected. Now, if that's the case, if that is the truth out there in the real world, and we run the experiment described at the beginning of the class, where only a sample of all of these unbiased supervisors were selected, is it reasonable to expect that the difference in promotion decisions made by the supervisors in the sample to be exactly 0? Because think about it, in the world it is, but I'm just sampling a piece of it, right? The answer, think about it for a bit, turn it off, and when you're ready, come back for the answer. The answer here should be no, right? And why? Well, because we live in a messy, variable world where our measurements, here the decisions of the supervisors, are pushed around by many factors in addition to the one we're paying attention to. Because of that, we should expect differences to occur between experimental groups and conditions due to factors that are other than the one we're emphasizing or even manipulating in the experiment. To repeat, in our specific case, the difference in promotion decisions between the two groups of supervisors is a sample estimate of the actual gender-based difference that could be expected to be observed in a population of all supervisors. The word estimate implicates the possibility of some error or variation due to chance, that in statistical jargon, we say it's subjected to sampling error. Classical example to build your intuition here. Imagine you want to determine if a coin is fair before getting into a bet. You throw it up in the air 10 times, and you find that you did not get the 5 heads and 5 tails as would be theoretically expected if the coin is fair. Why 5 and 5? Because, there are 2 potential outcomes, so I would expect half to fall in one, have to fall in the other. But imagine that the outcome was 6 heads and 4 tails. Would you be comfortable concluding that the coin is biased? And probably not, right? This deviation from the expected 5 head and 5 tail seem pretty plausible even for a fair coin, and could just happen by chance alone. If you get 8 heads and 2 tails, however, or 9 heads and 1 tail, you might be tempted not to trust that coin for a bet, because though this outcome could happen in principle, it is not very likely. Question is there any systematic way to make a decision about whether or not to reject the null, here the hypothesis that the coin is fair? And the answer is yes. And today my goal is to help you understand the scientist's strategy to do so, which is the process involved in statistical inference. So how do scientists decide whether or not to reject the null hypothesis? This decision rides on the answer to the following question, and the particular method to get there may vary, but regardless of the method, well, I should say most methods are based on that logic. Bayesian statistics a bit different though, but most classical statistical methods rides on this particular process. 1, could the data that I'm looking at plausibly have happened by chance if the null hypothesis were true, if nothing is going on? If the answer is yes, scientists do not reject the null hypothesis and assume that there is nothing going on. If the answer is no, it's not likely for me to see that big difference, the probability is very, very small, then scientists reject the null and assume that there is something going on beyond reasonable doubt. Now, how do scientists find out if a given pattern in the data could plausibly have happened by chance? Well, what they do is that they compare the pattern in the data they have with the pattern that would be expected under random conditions. That is, the pattern that would be expected if only chance was at play. With the coin example, let's say if you throw the coin up 10 times and you get 10 heads, you might start thinking that something is definitely going on with this coin. And in other words, you might start thinking that the coin is biased, which is the alternative hypothesis, and not fair at all. Now, we think that because we think that the coin is not fair because even though getting 10 consecutive heads might be possible, it's not a very typical or likely outcome if the coin is fair, if there is really a 50-50% chance of getting head and tail, right? If the coin is fair, there should be no difference, just like the promotion situation. Now, what is the actual probability of getting 10 heads in a row if the coin is fair? You know, if you get a coin that you know have been tested and is fair, what is the probability of me getting 10 heads in a row? Well, if the coin is fair, the probability of getting a head is 0.5 per toss. So the probability of getting 10 consecutive heads, given that the coin is fair, would be 0.5 times 0.5 times 0.5, 10 times, right? So 0.5 each toss. So it would be 8.5 raised to the 10th power. So let's see what this probability is. Look at that. It can happen, but look at the probability. The probability is 0.00097, right? So it's very, very small, very close to zero. Note that the probability of getting 10 consecutive heads, if the coin is fair, is not zero, which means it can potentially happen. However, the probability of that happening is so low, way less than the magical 0.05 that you're going to remember from undergraduate stats, the magic number, that you might be safer to conclude that there is something off with this coin and that you shouldn't use it for a bet. Let's try another one, right? So you would reject the null hypothesis that this coin is not biased. So this is basically the logic of statistics, right? And that takes us to the concept of a random experiment that I want to play with you to build your intuitions about statistical inference. So random experiment allows us to see how much a particular sample statistic gets pushed around by chance alone, that is, if the null hypothesis is true. Recall that in our case, the sample statistic is the percent difference in promotion decisions for an applicant based on their assigned sex. Assigned sex at birth. The results of the experiment showed a difference of 30%. The question that a random experiment should help us answer is, could the pattern in the data I'm observing plausibly have happened by chance? Here the specific question is, can a difference of 30% in promotion decision between the two groups of supervisors be plausibly expected if only chance is at play? That is, if the null hypothesis were true. If all managers were not gender biased, is it possible that we would get a sample, a random sample, right? And like with a random assignment to make these decisions for a female or a male file. Would it be plausible for us to expect a difference of 30%? So let's exemplify a random experiment to figure out this particular question. I almost want to change how I'm I'm recording to see if you can see me doing the experiment. So assuming the null hypothesis is equivalent to assuming that the actual difference in promotion decisions of males and females made by the referent population of supervisors is 0, right? That is the actual difference. We're seeing the difference greater than this in our experiment, but the different, but it's just by chance. The estimate of the difference obtained in the experimental sample, our 30%, is just not 0 due to chance alone, or more technically, sampling error. Now, if that's the case, it should be quite common to see a difference of 30% between promotion decisions for a male and a female file when we know for sure that gender is not at play under random conditions. A random experiment creates these random conditions. So let's see how this would play out for our gender discrimination study. So first, we know that out of 48 supervisors, 35 decided for promotion and 13 decided against the promotion. So step 1, to simulate what would typically happen if only chance is at play, you can grab 48 little cards or pieces of paper and put them in a hat, but 35 of them must say promoted and 13 of them must say not promoted. In other words, the overall distribution of promotion decisions in the hat must be the same as the one in the data set obtained in the experiment. If you're feeling lazy like me and you don't want to, get the little pieces of paper and write it out, what you can do is you can get playing cards. And what I did here, I got 35 playing cards that were black to represent a card written promoted. And I got 13 red cards to represent the not promoted decisions, okay? So now what you have to do is shuffle, right? Because if you put it in the hat, you're gonna shuffle the little papers and they're gonna get kind of randomly mixed. So that's what I'm gonna do here. I'll pause, shuffle, and then come back to do the experiment itself. I have completely shuffled the cards, and then we're ready for step 2, which is the following. I'm gonna pick these 48 cards in sequence, and I'm gonna put 24, the first 24 in one pile, which we will name female. That would be representing the random decisions for the female files, right? So here's the first advisor. What does he do for the female? Oh, promote. What does the second advisor did? Oh, not promote. What's the third advisor did for the female file? Oh, promote. Fourth, promote, so on and so forth. So let's do 24. And of course, this is random. There's no gender bias here, right? So I'm just making this up. So let me count 24 here on this back. And then I'll do 24 for the male decisions. So I stopped so I didn't have you look at me kind of doing this boring thing, but I put the first 24 cards were representing the decisions to promote or not promote the female file. And the second block, the decisions to promote or not promote the male file, okay? So if we count, and this is what I'm gonna do now, we'll see how many promoted cards is here on the female pile. So let me stop and count and I'll come back. On the female pile, I have 19 go ahead, promote the file. And I have only 5 not to promote. Now let's count what happened on the male files. I'll stop, count, and come back to tell you. So in this very random situation, I had 16 decisions to promote the male file and 19 decisions to promote the female file. So the difference in promotion decisions in this very random situation, note that it's not 0, it's 3. In the paper, the difference was 7, so that's smaller, right? And we'll compute what that is in percentage to compare with the 30% in the next video and see how we can use repeated versions of this experiment to compute the probability of seeing a difference of 30% under these random conditions, which is what we need to make an inference about the data that we observed in the paper, in this data set. See you then. Bye-bye.